Hello. In this video on ray optics, we will be discussing refraction. Now, this is the phenomenon of the bending of light from its path as it travels from one medium to another medium separated by a transparent interface. Now, this is the interface that we are talking about. This supposedly is separating medium 1 and medium 2, where the speed of light in the first medium was v1 and the speed of light in the second medium is supposedly v2. Now, there is a certain angle of incidence, of course, with respect to the normal that is considered at the point of incidence here. The point of incidence is O. The normal considered at the point of incidence is ON. And then as it travels from the medium 1 through the interface into the medium 2, then its path is changed and it now travels making an angle r with respect to the normal considered, where r is the angle of refraction. Now, in this case, the wavelength of light changes. As you can see, the velocity is changing. In the first medium it was v1 and in the second medium it is v2, with the change in velocity is brought about by the change in wavelength while the frequency remains constant. So the frequency of light remains constant. Now the wavelength changes. We'll come back to that after some time. Now we have laws associated with refraction, and those being, the first one being the angle of incidence, the sine of the angle of incidence to the sine of the angle of refraction. They bear a constant ratio which is constant for the given pair of media. So if we are considering the medium 1 and 2, they will always bear a constant ratio, the sine of the angle of incidence to the sine of the angle of refraction. Now this constant usually is termed, this will be a number, of course, and so we have this number to be associated with the refraction, and hence it is termed as a refractive index, and it is the refractive index of the second medium with respect to the first medium, and that is how we denote it. So sine of the angle of incidence to the sine of the angle of refraction is nothing but the refractive index of the second medium with respect to the first medium. Similarly, if the light was supposedly traveling from the second medium into the first medium, and if we are maintaining the angles, that is, we are keeping the angle of incidence in this case to be equal to r, while the angle of refraction, that has to be equal to I. And that is how we bring about the principle of reversibility. That is, if we are placing a plane mirror to which this refracted ray will be incident normally, then it will be reflected back in the same direction. It will be reflected back in the same direction, and maintaining the angle of refraction over here to be equal to angle of incidence, in this case being equal to r. Then the angle of refraction, as it will be moving over to the second medium, that will be exactly equal to I. Why? Because they are always maintaining a constant ratio with respect to one another, and that constant ratio has been settled with the kind of incidence and refraction angles interchanging. Now, as we are drawing this over a plane of a screen that you are observing right now, and me on a piece of paper, then what I find is that the incident ray, the refracted ray, and the normal that is considered at the point of incidence must lie on the same plane? Well, this is essentially because the light actually will take the least path that is available to it, so that for its propagation, and that is described properly by Fermat's principle, which we'll be dealing with in the um, degree level. But as of now, in this higher secondary level, what we observe is that what we know of the laws is that they all must lie on the same plane. In this case, the plane on which I have drawn the figure, or the incident, the refracted and the normal, all of them will lie on that plane. So these are the two laws of refraction. Now, moving over to the case of continuing with the case of refractive index, what we find is that when we are talking about the refractive index of one medium with respect to another, we also have the absolute refractive index. Now, the absolute refractive index is considered for a given medium, let us say for medium 1 in the figure given above, where the velocity of light is v1. Now, the absolute refractive index of any medium is its refractive index with respect to zero medium, that is the free space, which is air or vacuum. Now, this absolute refractive index for the medium 1, that has been taken in the figure above, then we can say that the refractive index of the medium 1 will be mu1 with respect to the zero medium, which is the free space, which is air or vacuum. We denote it simply by mu1, and that therefore will be equal to, now the refractive index is also given by the ratio of the velocities. Again, that can be proved by taking the trigonometric consideration that we have drawn in the figure. So sine of the angle of incidence to the sine of the angle of refraction will give me the velocity in the first medium to the velocity in the second medium. In this case, the velocity in air or vacuum divided by the velocity in the first medium, if it were the case. Now, if the light was traveling initially in air or vacuum, then it has traveled to the medium concerned, that is the first medium in this case, then its velocity in air or vacuum will be c, which is equal to 3 times of 10 raised to the power 8 meters per second, which is always the case. And v1 can be anything, depends on the medium that we have considered. So as of now, we are just denoting it as v1. So this is mu1. Similarly, we can have the velocity in the second medium and the absolute refractive index of the second medium as c over v2, and c being the same number, obviously. So when we say that we have the refractive index of the second medium with respect to first, we are therefore considering the velocity in the first medium to the velocity in the second medium, that being the ratio, which is also equal to, since the frequency remains same, supposedly we had the wavelength to be lambda 1 in the first medium and lambda 2 in the second medium, that multiplied with frequency will give me the velocity of the wave in both those mediums. Now lambda 1 and lambda 2 are different, obviously, but nu, that is the frequency, that is same, so we can strike that out and we simply have the ratio as lambda 1 over lambda 2. Now what we have also learned about the absolute refractive index, what we can also put over here is that instead of v1 over v2, what we can write is we can multiply a c over here and a c down below in the denominator. What that will do is we'll have a v1 over c and we'll have a c over v2. Now c over v1 would have given me mu1 as I have written over here. So V1 over C is obviously 1 over mu1. And then similarly, C over V2, as we can see over here, is mu2, that is the absolute refractive index of the second medium. Then we have a mu2 over here. So that means from all of this, what we can have is that mu2 with respect to 1 is equal to mu2 over mu1. That is the absolute refractive index of the second medium taken over the absolute refractive index of the first medium in the ratio. That is how we denote the refractive index of the second with respect to first. Now, in the same line, if we change the alter the definition, that is the absolute refractive index of the first with respect to the second, then it will give me the ratio of the absolute refractive index of the first with respect to the absolute refractive index of the second, and that is exactly the way we wanted it now, or exactly in the way it should be. So from these two, what we can write is that mu2 with respect to 1 will be equal to 1 over mu1 with respect to 2. So when we are taking the refractive index, now this is quite evident from the principle of reversibility that we have considered over there, because as I said, that when we consider the refraction where the second medium now acts as the first medium and the first medium now acts as the second medium, so in that case, with the same angles considered, that is, we put r as the angle of incidence now as the light travels from the second medium up to the first medium. So the angle of incidence being r, the angle of refraction in this case has to be equal to I, and therefore we'll have sine r over sine I. But the constant term that we will be getting right now in this case will be exactly the reciprocal of the constant as obtained over here, because we are changing the angles, we are interchanging the numerator and the denominator terms, and which is what we have obtained over here down below. That is the absolute, that is the refractive index of the second with respect to the first will have to be the reciprocal of the refractive index of the first with respect to the second. Now here's a question that I've prepared for you, so that we can understand what we have studied as of now. The question stands that calculate the speed of light in water if the absolute refractive index of water is 1.33. That's the first part of the question, which is what I'm going to attempt. So as far as the solution is concerned, so if we have mu of water to be equal to 1.33, now 1.33 can be also written as 4 over 3. Now this is nothing but the speed of light in air to the speed of light in water, and exactly what we have to obtain is speed of light in water. So we have that to be equal to, we cross multiply that, so we have c times of 3 over 4, 75% of the speed of the light in air. So that gives me, so that VW, that is the speed of light in water, is going to be equal to, this is 3 times of 10 raised to the power 8 times of 3 over 4, and that roughly comes out to be 9 over 4, that is 2.25 times of 10 raised to the power 8 meters per second. So that's the first question answered that I have provided. Now the second part of the question has that if the absolute refractive index of glass is a mu g, that is equal to 1.5, then we have to calculate the refractive index of glass with respect to water. As we know that refractive index of any medium with respect to the other medium is equal to the refractive index of the second medium, absolute refractive index of the second medium with respect to the absolute refractive index of the first medium. Now the absolute refractive index of glass has been given, that is 1.5, and that of water is 1.33. Now 1.5 can be taken as 3 over 2, and 1.33, as I have written, can be taken as 4 over 3. The reciprocal of that gives me 3 over 4. So that is going to be equal to 9 over 8, or roughly equal to 1.125, and that's the value. So that's the refractive index of glass with respect to water. Now if a ray of light is incident on the water glass interface, now first, because it has been provided water then glass interface, so obviously we are treating the water medium as the first and the glass medium as the second. So water glass interface at an angle of 60 degrees, then with respect to the normal, make sure that it is the angle with respect to the normal, because if it is not so, then you will have to consider the angle with respect to the plane and then take the other angle, the complementary angle with respect to the normal. But here it has been provided that the angle of incidence is 60 degrees with respect to the normal, so there's no problem with that. That is the angle of incidence, and we are to calculate its angle of refraction in glass medium. So what we have is the ratio sine I over sine R to be constant, that is mu of G with respect to water, and that will give me sine of 60 degrees in this case over sine of R, that is to be determined, and this one we can take this value. It will be easier rather than taking the decimal part. So this is 9 over 8. Now sine of 60, now sine of R is therefore going to be equal to sine of 60 times of 8 over 9. Sine of 60 is root 3 over 2 times of 8 over 9. 2 goes 4 times with 8. Root 3 goes 3 root 3 times with 9. So this is 4 over 3 root 3. Not only that, you have R to be equal to sine inverse of 4 over 3 root 3. You can keep it just like that in case you find it difficult to obtain the trigonometric value. The trigonometric table isn't available with you. The inverse trigonometric function can be kept as such for any unknown value or any non-general value that we have, which is this one. So this is how we determine the angle of refraction in this case. One more thing, and a very important one, the law that tells us that the sine of the angle of incidence bears a constant ratio with the sine of the angle of refraction. As we know, sine of the angle of incidence over sine of the angle of refraction is going to be mu of 2 with respect to 1, which is what we have obtained, mu 2 over mu 1. We can also write this as mu 1 sine I is equal to mu 2 sine R. This also can be written, and this is popularly the Snell's law that we come across in refraction. So Snell's law states that the sine of the angle of incidence to the sine of the angle of refraction bears a constant ratio, which is equal to the refractive index, and that is equal to the ratio of the absolute refractive index of the second with respect to the absolute refractive index of the first. My question: what is the absolute refractive index of air or free space? So the absolute refractive index of free space will therefore be equal to 1. Why? Because it is the ratio of the refractive index of air with respect to air. So that is why it has to be equal to 1. So because the reference medium here itself is in question, so that is why it will bear a constant ratio to be, which is obviously equal to unity with respect to itself. So that's it from this video. We'll be discussing more about refraction in the upcoming videos, especially the case of refraction through a glass slab and the real and apparent depth cases. Till then, thank you for watching.